breaking news here. We have a fire growing in downtown San Diego. It's represented by the function f of t. F prime of t is 0.3 e to the power of 0.6 t, and that's represented in square miles per hour.
Firefighters have begun putting out the fire at a rate of 6t, but they started at t equals 4. Alright, so when the firefighters arrived at 4 hours late, how big was the fire? So we calculated using the rate given, which is 0.3 e raised to the 0.6 t. If you do f of 0 plus the integral of 0 to 4 of f prime of t, then you would get the size of the fire when the firefighters arrived, which is f of 4. So then the f of 0 will cancel out with the negative f of 0 that integral creates, and then you just get f of 4, which is 5.012 square miles. And for how fast was the fire growing at 8 hours after it started, then we would just plug in 8 into the rate equation, but you would have to subtract the work, how fast the firefighters are putting out the fire at 8 hours, but then they start 4 hours late, so then it'd be 8 minus 4, because that's how long they would work. So it'd be t minus 4, so then when you plug everything in, it would be 0.3 e raised to the 0.6 times 8 minus 6 times 4, and that gives you 12.453 square miles per hour. And will the firefighters ever put out the fire? To solve that, we would set the size of the fire when the firefighters started putting out the fire, which is this, 5.012. You add it to the integral of from 4 to some number x when they put out the fire, of the rate minus the rate of the fire growing minus the rate at which the firefighters put out the fire, and if that equals negative 5.012, then that would make the fire be 0, the size of the fire be 0, so it'd be put out. So if you plug that in and solve for 0, you get 3 as an answer, so which is not greater than 4, so the fire will never be put out.
City Hall is infested by a hive of termites, represented by a logistic growth model. The maximum size of the termites is 10,000. Alright, okay, so here we're given a logistic growth model sort of thing with City Hall. Termites are infesting City Hall, and the carrying capacity is 10,000, so that's k equals 10,000, and k over 2 would be the point where the population starts decreasing. So the population is growing at a decreasing rate on the interval 5,000 to 10,000, and that's clearly illustrated here, where you have 10,000 here, and here it's starting to level off. This is part B, of course, and 50 is given as p of 0, so that's why it passes through 50 at when t is equal to 0. Alright, so moving on to part C, we're doing separation of variables, and then we're going to be taking the integral of both sides with p on the left and t on the right. So we're first given a new logistic growth model, p prime of t equals to 2t times p minus 1, and we're also given that p of 0 is equal to 3. now we replace this with this notation, and we multiply the dt on that side and put the p stuff on this side, so we get p's on one side and t's on the other. Then we do the integration. Notice here how if you do u subs, if you set your u equal to p minus 1, your du is still dp, so we don't have to worry about any of that stuff. And here, same thing. Yeah. And when you take the integral of 1 over p minus 1, you get ln of p minus 1. Don't forget your absolute values, and you just keep going down that way. You do e to the power to cancel out the ln's, and you're left here. And then you can drop down the c here, because e to the power of c is still c, it's just a different c. And you can drop the absolute values because c can be plus or minus. And yeah, so you don't need the absolute values to signify the positiveness. And at the end, when you're done simplifying, then we plug in p of 0 equals to 3. So p of 0 equals to 3. And bam, 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 you continue solving, and you end up with p equals to 2e to the power of t squared plus 1.